At the GAIR 2019 summit, Kazuhiro Kosuge, 2010 to 2011 president of the IEEE RAS, delivered the opening speech titled Coworker Robot PaDY as the first speaker of the robotics session. The speech focused on the integration of industrial collaborative robots and AI technology, analyzing the challenges facing the robotics field and the development opportunities brought about by the demands of various industries. Since then, Professor Kosuge has continued to expand in this direction, extending collaborative robot technology from rigid industrial assembly to the more challenging field of flexible manufacturing. At the upcoming GAIR 2025 summit, Professor Kosuge will present his latest research findings, an AI-based smart sewing system. This research continues his team's deep understanding of physical human-robot interaction and aims to solve the labor shortages and automation bottlenecks facing the global garment manufacturing industry. The sewing robot developed by Professor Kosuge demonstrates several breakthrough technical features. First, the system employs a fixture-free 3D sewing technology, using AI algorithms to automatically sew parts of 3D garment while keeping the fabric smooth and wrinkle-free. Second, through an innovative mechanism and optical sensors, the robot can detect fabric edges in real time and precisely control the sewing direction. Third, the system can be used without programming, allowing for rapid switching between different styles, sizes, and fabrics without the need for large-scale changes of molds or fixtures, making it particularly suitable for high-mix, low-volume flexible production. Finally, as a smart system for handling soft materials, its core sewing mechanism is enclosed within the machine, while external collaboration is performed by industrial arms compliant with ISO safety standards, ensuring safety in human-robot coexistence. On the eve of GAIR 2025, Leifone interviewed Professor Kosuge at the University of Hong Kong. The former IEEE RAS president chose to move to Hong Kong 4.5 years ago, recognizing its unique position as a hub connecting global innovation resources with the global manufacturing ecosystem. In the 6 years since his 2019 opening speech proposing the coworker robot PaDY concept, his team has finally transformed the vision of fixture-free flexible manufacturing depicted in that speech into a tangible, quantifiable, and commercializable technical entity. During the robotics session at GAIR 2019, Professor Kosuge used a comparison between the bustling streets of Shenzhen and the prediction curve of an aging population to reveal the sharpest contradiction of that era. When labor shortage becomes an irreversible social trend, how should robots evolve from cold automation equipment into true partners? At that time, his answer was PaDY, an industrial robot framework designed to achieve human-robot collaboration through the integration of AI technology. The core argument of that speech was insightful. The value of robots should not be limited to replacing repetitive labor, but should reconstruct the future of manufacturing across 3 dimensions: individual empowerment, social value, and international competitiveness. 6 years later, these concepts of programmability and environmental adaptability have taken a concrete form in Professor Kosuge's latest research. But this time, he aimed the technology at garment manufacturing, a field recognized by the global robotics community as the ultimate challenge in soft material handling. Professor Kosuge explains that the difficulty with soft materials lies in their infinite degrees of freedom. Before sewing fabric, one must first smooth out the cloth and place it in the proper position, which is also where previous sewing robots struggled. Professor Kosuge's sewing robot, however, accomplishes fabric smoothing through random actions. This is a stochastic process, and as the system is trained, they eventually learn how to smooth out these fabrics. This is precisely why the global sewing automation market still hovers at a single-digit automation rate in 2025. Professor Kosuge's team found in their research that even established industrial sewing giants in Germany and Japan rely heavily on template programming for their solutions. Even for high-value-added products like car seat covers, engineers need to spend weeks debugging trajectories, and the cost of changing fixtures remains high. In contrast, at efficiency-first contract factories and Dongguan, the first sample of the same product might be completed in just a few hours. Based on this, Professor Kosuge defined the goal of the Sewing DX project to research and develop key technologies for fixture-free and training-free operation and sewing and fabric processing. In 2022, when Professor Kosuge saw a smart cockpit concept displayed by a European car manufacturer at the International Robot Exhibition in Tokyo, he realized that car seat covers might be the best entry point to break this paradox. By 2028, the global automotive seat market is expected to approach $3 billion, with the sewing equipment market alone reaching $363 million. More importantly, car seat covers have three unique attributes: high production volume, high product value, and complex 3D curved surfaces that maintain regularity. These factors constitute the key to the commercialization of Professor Kosuge sewing robot technology. In the demo area, Kosuge first showed their new gripper, a seemingly simple passive end effector called PaDY, which embodies a disruptive design philosophy. When the robot pushes the end effector, the PAL grip, to the top layer of a fabric stack, only the top layer of fabric is picked up while the bottom layer remains in place due to a larger contact area and stronger friction. This passive design brings three advantages: significantly reduced gripper cost, no need for wiring or control signals, and adaptability to dozens of fabrics from cotton to silk by changing fingertip modules. But gripping is just the first step. The real challenge lies in aligning two different layers of fabric, such as in sewing scenarios with linings, and eliminating wrinkles. In another video, Kosuge demonstrated how they achieved this. A roll UP integrated with suction ports, actuation ports, and laser thickness sensors picks up fabric from both ends, rolls it up to deliver it to a designated position, and aligns the different fabrics. With its built-in fault tolerance and recovery system, a laser sensor monitors the thickness of the adsorbed fabric in real time. Once multi-layer adsorption is detected, the system immediately initiates a retry process, releasing suction, adjusting the angle, and readsorbing. Theoretically, the success rate is close to 100%. The ultimate test of all these front-end technologies is completed by that seemingly ordinary yet sophisticated sewing machine. Professor Kosuge's team spent 2 full years cracking the core control problem of the sewing machine's feeding system. It can be clearly seen in the video that at the moment tension is released, the originally wrinkled fabric is smoothed out as if by an invisible hand, and the edges align automatically to the predetermined position. In a paper published in IEEE Transactions on Mechatronics, the Kosuge team proposed an optimization method and designed a specialized controller to achieve system linearization, theoretically guaranteeing stability. This is precisely the underlying technology that enables their 3D sewing capability, by precisely controlling the rotational motion of fabric around the needle and pairing it with a vision system that detects in real time at 120 frames per second. The sewing machine is no longer a dumb machine that mechanically executes fixed programs, but rather an intelligent system that can dynamically adjust based on the fabric's actual position. This theoretical breakthrough makes 3D sewing possible. In another demonstration simulating the sewing of a car seat cover, the sewing needle traveled along the curved edge at a speed of 20 stitches per second, while high-speed cameras on both sides of the machine head continuously detected the fabric edge at a frequency of 120 Hz. At the Japan International Apparel and Non-Apparel Manufacturing Technology Trade Show 2024 in Osaka, Professor Kosuge completed the first public demonstration with this system. Several leading companies, including the EU's largest car seat manufacturer, expressed expressed strong interest. Although traditional giants appear cautious in their investment decisions, the technology demonstration has triggered close attention and strategic maneuvering from top European car companies and sewing equipment manufacturers in China and Japan. The core logic behind the company's caution is simple yet sharp. If this technology truly has disruptive competitiveness, why haven't other companies deep in the industry for decades achieved it first? When analyzing the competitive landscape, Professor Kosuge admitted that current fixture-based solutions for sewing robots have dominated the market for over a decade. As vested interests, their business model is built on the sales of NC sewing machines using templates, where revenue is directly linked to system complexity. This might be the fundamental reason for their reservation towards breakthrough technologies. A more realistic challenge comes from the cost structure. When asked about the most expensive component of the system, Professor Kosuge told us that the computer system is the costliest part, and that doesn't even include software licensing. In addition, the mechanical structure, sensing system, and controller also represent significant costs. However, Professor Kosuge insists that the real advantage of the system lies precisely in its ability to disrupt the cost logic of traditional automation equipment. In the interview, he repeatedly emphasized two keywords: no programming and affordable. These two characteristics pave the way for a lightweight business model. A more critical breakthrough may lie in the scalable design of the business model. The system characteristics repeatedly emphasized by Professor Kosuge in the interview, operable without programming and adaptable to different forms of robot hardware, actually lay the technical groundwork for a lightweight pay-as-you-go business model. This technical architecture leaves room for more flexible business models. In the future, it is even expected to adopt a service model of selling sewing capability rather than selling equipment. Factories do not need to invest huge sums of money to purchase the entire system at once but pay service fees based on actual sewing volume. Under this model, corporate decision-making costs will be significantly reduced, and barriers to system adoption will crumble. In Professor Kosuge's vision, sewing robots are not meant to replace sewing workers but to empower them. In the future, they won't need to master complex sewing skills. They only need to complete loading/unloading and quality inspection to keep machines producing 24 hours a day. As he said in the interview, their goal is to empower workers, not reduce them. Despite the bright technological prospects, Professor Kosuge still faces severe challenges. First is the limit of the technology itself. The team is trying to use transformer models to solve the dynamic planning problem of soft fabrics, but collecting training data is extremely difficult. The friction coefficient and elastic modulus of every piece of fabric are different, and traditional simulation cannot reproduce the complexity of the real world. Second is the game of capital and talent. Professor Kosuge plans to complete financing as soon as possible to recruit software and mechanical engineers and achieve the output of the first batch of products within 1 to 2 years. Finally, there's market acceptance. While the 2024 Osaka demonstration attracted interest from several companies, converting that interest into investment remained challenging. As of the interview, Professor Kosuge remains patient, believing that although the decision-making cycle in manufacturing is long, the market window won't wait indefinitely. The market analysis he presented shows that minimum wage levels in EU countries continue to rise, and labor costs in traditionally low-cost regions like Slovenia and Romania are also growing rapidly. At the end of the interview, Professor Kosuge insisted on taking us to another building to see the complete system demonstration. Walking through the corridors of HKU's Centennial campus, the setting sun cast long shadows, much like this 4-plus-year journey of R&D. In the lab, a sewing machine was sewing a car seat cover sample at a speed of 20 stitches per second. The robotic arm gently flipped and aligned the 3D curved fabric, and the only sound was the hum of servo motors. When the final product was handed to us, its quality was virtually indistinguishable from manual sewing by a technician. In his speech at the 2019 GAIR conference, Professor Kosuge stated that robots should make manufacturing more human. Today, we see this humanity manifested in liberating workers from repetitive labor to do more creative work, freeing enterprises from cost competition to pursue higher quality development, and allowing society to move beyond demographic anxiety to embrace a technology-empowered future. On the opening keynote stage of GAIR 2025, Professor Kosuge will present the sewing robot to the world, showcasing the 6-year promise of the IEEE RAS president. From PaDY to smart sewing, from collaborative concepts to commercial entities, from Hong Kong labs to world factories, this hard-tech battle over soft materials might be a microcosm of China's transition to intelligent manufacturing. In this transformation, what is most valuable is the persistence of a top scholar amidst skepticism. True innovation lies not in the complexity of technology, but in whether it allows the most ordinary laborers to share the dividends of technological progress.